take a look at this question here. This is what we are going to be working through today. So, in 1959, Littleton and Bondi suggested that the expansion of the universe could be explained if matter carried a net charge. Suppose that the universe is made up of hydrogen atoms with a number density n, which is maintained a constant. Let the charge on the proton be EP, which is given as an expression, that is minus 1 plus y times E, where E is the electronic charge. We have to find two things. Find the critical value of y such that expansion may start, and show that the velocity of expansion is proportional to the distance from the center. This is a question from the NCE exemplar problems in physics, class 12. Now, why I chose to illustrate this particular problem is because this is definitely a very innovative and research oriented problem, which will not only make you go through the entire process of creative thinking, out of the box approach of solving problems. This will also ensure that you learn something new. And let me address the elephant in the room. This problem might not be appropriate for plus 2 students, but it is definitely something which I hope you will be able to understand if you are well conversant with the fundamentals of the electric charges and fields, for that matter, and some basic high school mathematics will do. And yeah, let us dive into this wonderful adventure of exploring and figuring out some sort of way to solve this problem. And by the end of this video, I hope this will be a little bit clear to you about how to approach and attack this type of problems. So here, if you notice something, that this problem needs a bit of what we say, some sort of theoretical background before directly proposing it or giving it to the students. By which I mean that if you notice, two names come up, Littleton and Bondi. Well, they are very famous physicists, or rather cosmologists, who propounded various theories about the universe and how things started and all that. And in particular, this particular, you can say, sort of their quest to frame a problem or some sort of theory or about some sort of universe in which they have a net charge, the matter which makes up their universe has some net charge. This type of approach was to support the theory of universe which was proposed by Hubble. You must have heard this name. Hubble is again a famous scientist after whom the Hubble Space Telescope has been named by NASA. So Hubble suggested that if we have some sort of observer which is moving away or receding away from us with some velocity, then that would be something evident that basically he suggested, so as to say that the observable universe is expanding. And this expansion was explained by him in simple terms involving observer and some sort of mass particle which is going away from the observer, so which suggests that the universe is expanding. The expansion of this universe, when mingled with this type of a concept called electrostatics, becomes very interesting, that you will be indulging yourself in solving a problem which might establish the fact that the universe is expanding. And here in particular, let me give you some background about the fact that you must have encountered this particular this thing. To increase the thickness, yeah, this particular expression you might have encountered here. Well, this definitely deserves some sort of explanation before we jump into the solution of this problem, and I'm going to show you where this is coming from. So this is not described here, why this comes up all of a sudden out of the blue. And then so that might be a point of confusion in understanding this problem in the first place. If I read it again, in 1959, Littleton and Bondi suggested that the expansion of the universe could be explained if matter carried a net charge. Now, it is worthwhile to note that in our universe, matter is electrically neutral. It does not carry a net charge. But in their universe, they propounded that matter has to carry a net charge, which would justify their theory of expansion of the universe. Now, suppose that the universe is made up of hydrogen atoms. They have simplified things by giving the basic fundamental constituents of their universe as hydrogen atoms. So their universe is filled up with hydrogen atoms, which are having a number density n, which is maintained a constant. This is given. Now, in their universe, the charge on a proton, as you can clearly see, is exceeding the charge on an electron, which again justifies why in their universe matter carries a net charge. Because in our universe, proton and electron have the same electronic charge and they only differ by a sign. But here it is something different. So let me give some background from where does this expression in yellow comes from. So this is something which I thought they would give in their problem, but unfortunately they have not added this part, which would make it a more descriptive and complete problem, I believe. So let me shrink this and let me use the space available here. Yeah. So so now I begin. Basically, they have assumed that the protonic charge, say, which is EP, is much more than their electronic charge. And let me, yeah. So the let me denote the protonic charge as EP. So this exceeds the electronic charge. So let us say the amount by which it exceeds the electronic charge is EP minus E minus, where this E subscript minus denotes the electronic charge on an electron. This is charge on a proton. So this is the amount by which the protonic charge exceeds the electronic charge when divided upon the electronic charge. This ratio is named or labeled Y. So you see, this expression basically gives us a variable y, a constant y, let us say, which is signifying the amount by which the protonic charge is exceeding the electronic charge as a ratio. So this is basically a ratio. The y you see here is a ratio, which is basically the fraction or the ratio by which the protonic charge is more than this electronic charge. Now if you rearrange this expression, then and write it in terms of protonic charge as a as in terms of y, it becomes E minus times of y plus E minus. Now we all know the charge on electron is, if we are denoting it as E minus, then the charge on an electron is minus of E, where E is 1.6 into 10 to the power of minus 19 coulombs, which is the fundamental block of electronic charge. So this is the, if we substitute this here, so we will get that expression of protonic charge on a proton in the universe of Littleton and Bondi. So you get this expression, and that basically justifies where on earth the expression in yellow comes up. That basically justifies it. Now if you take a closer look, so I hope this part is clear. This is the background which should have been given, and basically this theory of Littleton and Bondi about matter carrying some net charge to just to explain the expansion of the universe by solving this problem, you can say, is in always supporting the theory given by Hubble. Hubble's theory about the expansion of the observable universe is basically being heavily supported by this type of a problem, and you will understand what I'm trying to say after we solve this problem. So this is basically the background which should have been mentioned in the problem, which makes it a bit of kind of deficient in information, like this part should have been mentioned. So this is what was missing, so I've mentioned it. Now we can go back to the problem and begin our approach. So here we have some information to process, and apparently it might be a bit hard to comprehend at the first glance. That is, but we need to simplify things, and they have already simplified a lot of things. So we are required to find the critical value of y. I hope you know what is that y. It is basically a ratio which defines by how much the protonic charge exceeds the electronic charge in the universe of Littleton and Bondi. Because remember, in our universe they are same. So let the charge on the proton be this they have given. So find the critical value of y such that expansion may start. So expansion, by expansion they mean the expansion of the universe of Littleton and Bondi. So we have to find the critical value of y. Now before beginning, we need to write down certain things as in custom to get things very clear. So erase this part here. So here I would like to say something. You can start here. Yeah. So the number density of hydrogen atoms, let me type it. Number density, oh, that's in black. Sorry. Yeah, the number density of hydrogen atoms that equals, that is basically our n. It is given in the problem. And this is a constant, right? Number density of hydrogen atoms. I've made a mistake over here. Uh, anyway, that's density. So that is n. Let me delete it. So we have n. It's better to write than to. So n is the number density of hydrogen atoms. It is a constant. So now if we think about the charge on a proton, these are the things which are given. Charge on a proton, that is given by the equation, which is ep equals, which I just derived a while ago, 1 plus y times of the fundamental electronic charge E. This is the charge on a proton. So we have to find the critical value of this y for which the expansion of the universe starts. Now, before we begin solving this problem numerically, we need to make an assumption. We have to, you must have noticed that we do not have a physical picture of the universe. If I consider the universe as a macroscopic object, then I need to ascertain a sort of physical shape, so as to say, to simplify things and to get a picture of what exactly is happening. How do we quantify the expansion of the universe? So basically I assume, for simplification, let the universe be a sphere of radius r. That perfectly works out. Let me see if I have a sphere over here. You can do with this thing. Yeah. Change the color to, like, make it a ring. Yeah, so the universe is a sphere of radius r, And so here we have given a physical shape to this universe. So it is a sphere of radius r, and it is a homogeneous sphere. By homogeneous, I mean the hydrogen atoms which are constituent of this universe. Basically, they make up the universe of Littleton and Bondi. So these hydrogen atoms are uniformly distributed in this universe. Now, talking about hydrogen atoms, what is the charge on a hydrogen atom? Like, now we should be able to find that out. We have the information about charge on a proton. We know the charge on an electron is E. So what is the charge on a hydrogen atom? The charge on a hydrogen atom, let us denote that as QH. Charge on a hydrogen atom by this symbol, it becomes the charge on a proton, which is minus 1 plus y times of E, added with the charge on an electron. Because you see, a hydrogen atom is made up of one electron and one proton. So this is the charge on one electron, this is the charge on one proton. So this translates to the charge on a hydrogen atom. And if you solve this, you see this cancels out as and simplifies as minus ye. Talking about magnitude, if I give a mod, if I talk about the absolute magnitude, then it becomes y times of E. This is the charge on a single hydrogen atom, which is the fundamental building block of the universe of Littleton and Bondi. Now, if we have obtained this much, let us understand what they are trying to say by expansion. So, picture that there is a, kind of, there is a hydrogen atom at the surface of this universe. Okay, this is the hydrogen atom at the surface. Now, due to the electric, now the hydrogen atom is carrying a net charge, right? So, which means that in the universe of Littleton and Bondi, matter carries net charge. So, this hydrogen atom at the surface of this sphere will be having some net charge of Ye. Similarly, all the other hydrogen atoms which are making up this universe will also have this fundamental unit of charge on them, because in Littleton and Bondi's universe, as stated in the problem, they carry some net charge. So now it is very easy to realize that those charges will repel this hydrogen atom in this direction. Or, in other words, we can say that there exists a definite electric field at the radial distance r at the surface of this sphere, right? There exists some electric field. So now let us denote that electric field as ER. I mean the electric field at the surface of this sphere. Let that be denoted as ER. Now we know that to find this type of electric field, we can use what is called Gauss's law of electrostatics, like Gauss's law for some sort of charge distribution. You see, these hydrogen atoms are no longer neutral atoms, they have some charge of Ye. So they make up the universe of Littleton and Bondi, and which means if I put some charge at this point at the surface of the universe, which is a sphere here, then they will experience that will experience a force because of the electric field. So the electric field at the surface of the sphere is what we want to find out. We can use Gauss's law. Let me write it out. So, Gauss law. Gauss law of electrostatics. What does Gauss's law of electrostatics give us? Well, Gauss's law of electrostatics basically helps us to find electric fields or any such thing by this expression, we all know, we are familiar with it, that the surface integral of the electric field times the elementary surface vector of the Gaussian surface considered equals the net charge enclosed by the Gaussian surface upon the constant epsilon naught. Now here in this expression, I mentioned the term Gaussian surface, so that means I need to assume a Gaussian surface for finding out this electric field at a radial distance r for the universe which is assumed to be a sphere, right? So that means, let me draw the Gaussian surface. So that means basically the Gaussian surface is, oh sorry, that is, yeah, the Gaussian surface is basically something like this. The Gaussian surface is a sphere enclosing the sphere of the universe. And you see the q appearing here, the q appearing here, this q is the net charge enclosed by this Gaussian surface. So first let us find out what is the net charge enclosed by this Gaussian surface. It is basically the total charge of all the hydrogen atoms which constitute this universe, right? Because that universe is made up of only hydrogen atoms. So let us try to find out q. The q is, okay, you go about this in this way. First, the number density comes up, which is the number of hydrogen atoms per unit volume of that sphere times the volume of the sphere, which is 4/3 times pi times the radius cubed times the charge on a single hydrogen atom, which is y times of E. So you see number density of hydrogen atoms times the volume of the sphere times the charge on a single hydrogen atom gives us the net charge enclosed by the Gaussian surface, which we have considered here. Now if we put back and you see what is this quantity ds, the when this surface integral is performed over ds, you see the Gaussian surface is a sphere. It is drawn in an arbitrary way, but it is a sphere. It might be a bit irregular here, but it is a sphere, right? So the surface area of this sphere is 4 pi r square. So we can write it as electric field at the radial distance r times 4 pi r square, that equals this charge q, which is n times 4/3 let me do the math, times ye, right, upon epsilon naught. So if I solve this equation, then my 4 pi's cancel, this cancels with a index here, so I am left with the expression for the electric field at the surface of the sphere, which is n times of r times of ye upon 3 epsilon naught. This is the expression of the electric field at a distance r from the center of the universe, right? This much I hope is clear. Now we go back to that sphere. Let me remove this Gaussian surface. Now you see that this This is the universe. It is having hydrogen atoms as the only constituents. Like our universe has a lot of things, but there the universe described by Littleton and Pondy, to simplify things, has been assumed to be made of only hydrogen atoms, so that the analysis is simple. So that means the hydrogen atoms do have some mass. And when I talk about mass, mass is associated with some sort of gravitational field. And then in the picture comes in the gravitational forces of attraction, right? So if you think about this uh, hydrogen atom here, then it not only experiences the force due to electrostatics, it also experiences a gravitational force of attraction which is pointing radially inwards towards the center of the universe. Let us name that as Fg. So this force is due to the fact that the universe is made up of hydrogen atoms which have some mass, and this is a hydrogen atom of some mass, say I denote it as mp, mass of this hydrogen atom. So that means this mass is attracted by the total mass, let us denote that as m, the total mass of the universe, and it is a force of gravity which is pulling it towards the center of the universe. This gravitational attractive force is something which will give us a new interesting dimension to this problem. And basically, by expansion of the universe, we mean the electrostatic force of repulsion must be greater than the gravitational force of attraction by virtue of the masses. So basically, that would give us some sort of expansion of the universe, some sort of linear radial increase in the R, right? So, which means that we have to then solve this. Now, in doing so, let us first find out what is the total mass of the universe. And it is very easy to do so, given we already found how to find out the total charge of the universe. So to find the total mass of the universe, let us denote the total mass of the universe as m. Oh wait, one thing you might be thinking all this while, that why all of a sudden I'm trying to find out the total mass of the universe. That is because here we applied Gauss law of electrostatics to find the expression of electric field due to the charges which are trying to push this hydrogen atom which is electrically charged. Similarly, there is, and this is the interesting part of this problem, which you are gravitation. Wow. Gauss's law for some sort of mass distribution. Here you have Gauss's law for some sort of charge distribution, which was uniform in this case. So here we have Gauss's law of, let me give you some sort of brief intro about it. What is this thing? So it is Gauss as I mentioned previously, there is an analogous law of Gauss for masses. Here it was charges. See, in electricity, charges are analogous to mass in mechanics. So basically, there is some sort of Gauss's law of gravitation. Wow. Gauss's law for some sort of mass distribution. Here you have Gauss's law for some sort of charge distribution, which was uniform in this case. So here we have Gauss's law of, let me give you some sort of brief intro about it. What is this thing? So it is Gauss Now, what is this Gauss's law for mass distribution? Right? Let me, yeah, Gauss's law for mass distribution. Basically, you see the M I wrote here. So basically, we have a law which is very similar to Gauss's law of electrostatics. Here in electrostatics, we are dealing with some sort of electric field, and we are performing a line integral, a surface integral over these two vectors we have taken elementary area of the Gaussian surface, differential area over the Gaussian surface, and then there is some net charge enclosed by that surface, some constant appearing in the denominator. Similarly, very similarly, we have Gauss law for mass distribution, which means here again, before applying this law, we need to draw we need to draw a Gaussian surface and then operate this law. So let me draw the universe again. Say this is the universe. Yeah. So here we have this universe of radius r, and this universe of Littleton and Bondi has been assumed to be a sphere of radius r, as you know from the beginning. So here we are very much aware of the fact that this universe is made up of only hydrogen atoms, and you know, these hydrogen atoms have some mass. So which means that if I keep a hydrogen atom at the surface of this universe, so that will experience some gravitational force of attraction. And this is where this type of a force is different from the electrostatic force. See, in electrostatics, like charges repel each other, unlike charges attract each other. So you get two types of forces. The nature of the force can vary. But in gravitational domain, all the forces are attractive in nature, which is why we assume a Gaussian surface like let me draw it in red, I guess will be better. So we have a spherical Gaussian surface here. I know that is not a sphere and it is one of the most terrible things I have ever drawn, but then assume it to be a sphere. We are good physicists, so we can assume anything for that matter. So this sphere is enclosing this mass m, right, which is the total mass of the universe. So we write the Gauss law for gravitation as the surface integral of the gravitational field. It is written like this: it is a vector quantity times the differential area vector, that equals minus 4 pi gm, where m is the total mass of the system enclosed by the Gaussian surface considered. Here it is the red sphere. It is enclosing this mass m, which is the total mass of the universe. And this g, so basically if I work out, it becomes g. Now I need the gravitational field at the distance r from the center of the universe. I need this. I need I need the gravitational field intensity at the radial distance r from the center of the universe at this distance, right? So which means that I can write this. I can write this as g subscript r, which means the gravitational field at the radial distance r times what is the surface integral of this differential area vector of this Gaussian surface. It is basically the surface area of this sphere, which is 4 pi r square. Now you might ask here, before I proceed further, why a negative sign is appearing here. See, this is because of the fact that the gravitational force is attractive in nature. You do not have some sort of gravitation which will make masses repel each other. It is from the universal law of gravitation that we understand this fundamentally, that all sorts of masses will always attract each other by virtue of their gravitational attraction. And then there is this interesting concept of gravitational collapse, which means that if masses attract each other, then they keep on attracting each other. So we have when we solve this, gr, which is the gravitational field at the radial distance r in the sphere, times 4 pi r square, that equals minus 4 pi gm. Here you must have observed that how this Gauss law for mass distribution is analogous to Gauss law for charge distribution. As in, you see the 4 pi g term is a constant on the RHS of this equation, and it is very much analogous to the term epsilon naught appearing in the denominator of this Gauss law of electrostatics. Similarly, the charge in Gauss law of electrostatics is very much analogous to the mass of the system enclosed by the Gaussian surface. See, we define both of them along similar lines, that a common framework is there, and basically both of them they fall into that framework. They perfectly fit into that frame, which is that some sort of quantity will be enclosed by a Gaussian surface, and then we take some surface integral of some field which is due to that quantity. So for charges it is field, for electric field, and for masses it is gravitational field. So now that is how both of these are similar, and that is basically the power of this type of the unified theoretical framework, which is bringing in or you can say which is making both electrostatics and gravitational picture fall in one frame. This is basically the beauty of this problem. Now we need to, before further proceeding, we need to find the total mass of the universe, which is, again, if I take the mass of one hydrogen atom as mp, then the total mass is the number density, which is the number of hydrogen atoms per unit volume of the universe, times the volume of the universe, which is 4/3 pi r cube, times mass of a single hydrogen atom. So this is the total mass. So if I plug this in, so I get the expression of the gravitational field at the periphery of the universe. Let me just plug it in. I have this privilege of putting things like this, so that basically eases out the pain of writing with a mouse. There is some sort of perk of using this. So now these 4 pi's cancel, and this goes with a index, so we are left with now. If I consider the magnitude of this gravitational field, then I can omit this negative sign, this sign appearing here. I am not writing it, I am considering the magnitude of this gravitational field. So that means, that basically means yep, we have obtained the expression for the gravitational field at the periphery of the universe. We have obtained the expression of the electric field at the periphery of the universe. So now, due to this gravitational field and due to this electric field, the hydrogen atom kept here is going to experience a electrostatic force of repulsion, that is denoted as Fe, and a gravitational force of attraction by virtue of mass of all the hydrogen atoms which constitute the universe. And for the condition of expansion of the universe, it is very much evident that this force, which is pushing the hydrogen atom outward, radially outward, must be greater than this force which is basically pulling it in radially inward. So that translates to the electrostatic force being greater than the gravitational force, and the limiting condition becomes the two forces equaling with each other. Now let us try to find out these two forces, and I hope you are now at par with this much. So by this equating these two terms, we will basically get a condition, some sort of value of y for which the expansion of the universe will start. So for the universe to expand, first we need to find this force electrostatic force of repulsion, which is the charge on a hydrogen atom times the electrostatic field at the periphery of the universe. This is the force, and the force is a vector quantity. So we write it like this, a more accurate way of describing. And the gravitational force of attraction, that is also a vector, but it is attractive in nature. That is the mass on, of a hydrogen atom times the gravitational field at the periphery of the universe. So we need to equate these two forces, and that gives us the condition of the just the limiting condition at which expansion of universe starts. Basically, this guy tries to one up this one, and this limiting condition is them just equating out with each other. So we write that that equaling condition, the limiting condition, which is of prime importance here. So it becomes the two forces becoming equal for the expansion of universe. So ye times the electric field, so that is a vector equation. So mp times the gravitational field, and we plug in the respective values of these expressions. So that gives us, let me pick them up from here. Let me see if I can totally pick this up. No, NRYE. Okay, let me write it down. That's the best thing. Yeah. So that becomes, if you solve this, R N Y square E square by 3 epsilon naught. This equals with 4/3 pi R G N, which is the number density, times mass of a proton squared, because they appear two times. So that translates to, what does it translate to? Y square. See, you see these terms are cancelling out. And anything else? No. So that translates to y square as 4 pi 4 pi g mp square epsilon naught, and the 3's cancel on both sides. I missed this. So by the electronic charge squared. So I hope this much is correct. 4 pi g mp square times epsilon naught by the. So now we can easily write it like this, the final result. So we are almost near our solution. 4 pi epsilon naught g, and then we have mp e raised to the power of 2. You see, this is a constant, and we already know the mass of hydrogen atom, electronic charge, so all of these are constants. So that gives us the exact value of y. Let us say the critical value is denoted as y subscript c, for which expansion starts. It would be appropriate to make this almost equal. So that becomes the value I got. and it is almost of the order of 10 to the power of minus 18. So the critical value of y at which expansion of the universe starts is of the order of 10 to the power of minus 18. So this is our answer to the first part of the problem, and let us get back to the problem. Sorry, let us get back to the original problem. Yeah. The second part says that show that the velocity of expansion of the universe is proportional to the distance from the center. So velocity of expansion is proportional to distance from the center. How do we go about solving this? So again, it is very easy to do that at this stage, because I hope you have almost understood completely what is happening, circles of physics. Basically, they are saying, so to do that, we can write Newton's second law as in the net force which is acting on that hydrogen atom at the surface of the universe. What is the net force? It is basically the electrostatic force minus the force due to the gravitational attraction force due to the masses of the hydrogen atom. This is the net force that equals mass of a hydrogen atom. This is the net force on that hydrogen atom. This is mass of that hydrogen atom times acceleration. Now what is acceleration? It is d2r times dt2, which means it is the second order derivative of the radial distance r, which is the radius of the sphere, because that mass is going to accelerate in a radial direction described by the radius r. So this is the expression of Newton's second law. Net force is mass times acceleration. So this is the force which is acting on this mass particle mp, which is that hydrogen atom, times the acceleration. Now if you plug in the values of this difference, you will get something like, I write this thing in the LHS. So mp times second order derivative like this, that equals the difference of the forces, which is one third n y square e square r upon epsilon naught minus 4 third pi g, and then we have n mp and r, I guess. Yeah, what was that force r due to gravity? It was this much in mp, and then square n mp square, basically this. And remember that this force, we have considered the magnitude of the force, because otherwise this would become a positive sign, because already there was a negative sign associated with the gravitational field at the surface. So we have omitted that negative sign because we are only considering the magnitude of the gravitational field, and hence correspondingly the force is also positive. So that is why this expression comes up. Now here, if you solve this, type of a thing, basically you can take the r common from both sides. I hope there is a r appearing. Yeah, there is a r which I missed. R is there. So here the r was there. So we can take the r common, and basically mp times d2r by dt2, this equals r times whatever this expression comes. You can do that, whatever comes after taking common. So now the second order derivative of r, that becomes r times of that expression by mp, mass of a hydrogen atom. So now see, this is a differential equation. So we need to solve this differential equation to proceed further. So you see, the solution of this differential equation, if you remember, will be of something like r equals a e to the power of minus a e to the power of alpha t plus b e to the power of minus alpha t, where let alpha be this constant. You can assume this to be the constant alpha. Basically, d2r by dt2 equals r alpha. So the solution of that differential equation is given by this. And here, for condition of expansion of universe, the value of b is 0. A and b are some arbitrary constants appearing in this solution. So value of b will be 0 for the condition of expansion of universe. That is, for the universe to expand, there cannot be any negative velocity is always increasing. For universe to expand, it is radially increasing. So that gives us that leaves us no room for this type of expression, so that cancels out, and so we are left with we are left with the expression as r equal to a e to the power of alpha t. Now if you differentiate this once, what do you get? Dr by dt r dot, that equals a e to the power of alpha t times this quantity alpha. Here in this expression, you can clearly see that this is the velocity. See, for increase in radial distance, the radius, the velocity is dr by dt. This is the velocity of expansion, right? For this sphere, if the radius is increasing, so the velocity of expansion is dr by dt, and that does depend on this quantity. So if we go back to the problem, show that the velocity of expansion is proportional to the distance from the center. Yes, it is definitely proportional to the distance from the center. That is what we just got. That the velocity, which is r dot, is proportional to the distance from the center. Distance from the center. From the center. Oops, it's too bad. From the center, yeah. This is the velocity of expansion, radial velocity of expansion. It is proportional to the distance from the center. Hence, proved. With that being said, I think you can get through this, and I hope that this video definitely made an attempt to simplify this problem as much as possible. Thank you for watching, and don't forget to subscribe the channel.